Hello, class. So on this video, we'll continue on section 5.2, where we're talking about definite integral. So in the previous videos, we saw how we used this notation for a definite integral. What was a definite integral? Well, it was net area. And we went over how we can approximate net area using the same algorithm that we had for approximating area in general. The only difference was that when rectangles were on the bottom, we subtracted that area. But that came out naturally with the function being negative. Okay. Now, then we mentioned that, of course, the more subintervals we use, the more accurate approximation is going to be. So that's how we came up with this definition here. If we look at the limit as n approaches infinity of this sum, which is just an approximation using m subintervals. Okay, so we take the number of subintervals to approach infinity, and then notation-wise, we define that as the definite integral using this integral symbol, right? Integral from a to b of f of x dx. Right? So of course, we also talked about how that notation looks very similar to the indefinite integral, but it's not the same. Right? The indefinite integral, which is the same symbol, but without the endpoints of the interval on the s sign, or the integral sign, that meant all antiderivatives. So then we said, well, of course, there's a relationship between both of them if we use the same, almost the same symbols. I will get into that later. The last example we did was just seeing how to rewrite net area as a sum. So going from sum to integral notation. I basically put the intervals on the endpoints. Whatever's inside after the sum, that's your function, and then you change the change in x symbol, or delta x, by dx. That was the last video. Now in this video, we're going to use a little bit of geometry to evaluate definite integrals. For example, let's look at part A. We want to find the definite integral from -4 to 2 of 2x plus 4 dx. By definition, this is the same as the net area bounded by f of x and the x-axis on the interval -4 to 2. So if we want to find this geometrically, right, we want to find this net area, well, let's graph it and see what this region looks like. That's the first thing we should do. Okay. So what's the graph? It's 2x plus 4, all the way from -4 all the way to 2. So let's go to another page just so I'm sure we have enough space. So let's do 1, 2, 3, -1, -2, -3, -4, and then the function of here. Let's go 1, 2, 3, 4. I think this is enough, and then -1, -2, -3, and -4. Okay. So the function was 2x plus 4. Yeah, so this won't be enough, unfortunately. Let's go another way to 2. We need to go all the way up to 10. So let's go 5, 6, 7, 8, 9, 10. Okay. So what's this function? Let's just plot it. It's a line, right? Well, if you want to graph a line, just graph 2 of the points on it and connect them, okay? So let's just plot the endpoints. What's the function? So remember, the interval is -4 to 2. So what's the function value when x equals -4? Plug in x equals -4. You get -4 times 2 is -8. Plus 4 is -4. So we get the value -4, -4. And then when x equals 2, you get 2 times 2 is 4. Oh, yeah, we're only to 2. Okay, yeah, so we were good. So 2 times 2 is 4, plus 2 is 8. So we actually only go up to 8. So 5, 6, 7, 8. So up to here. And then that's the graph. So let's now connect the dots. It's not going to be an exact picture. That's fine. But that's the idea. That's the graph. So if we're trying to find the net area bounded by this function, what is that we're looking at? We'll just see the area bounded by this in the x-axis. So here, we're looking at this area. Here, we're looking at this area. Okay, it should be 2. Let's say it's 2. Now we want to calculate that net area. Right? Remember that all that means is that when the area is below the x-axis, you make it negative. When it's above, you make it positive. Okay. Well, this should pass through -2. Also, how do we do it? well, we want to do it geometrically, so we just notice that what we have here is two triangles. So we can just use the formula for the area of a triangle. We have a triangle here underneath the x-axis, and we have a triangle here above the x-axis. So what are the areas? Well, we have to do 1/2 base times height. So let's name this triangle here T1. Let's name this one T2. So what's the area of T1? Well, it's going to be 1/2 times the base. Well, the base, we can say it goes from -4 to -2. So I'm doing the horizontal side as the length of the base. So that's a base of 2, right? -4 to -2, that's a length of 2. Then what's the height? Well, it goes from the x-axis all the way down to -4. That's 4 units. So the area total is 2 times 1/2 is 1, times 4 is 4. So that's for the triangle T1. Now let's calculate the area triangle T2. Using a similar thing, 1/2. Again, for the base, I'm going to use the horizontal part, so what's on the x-axis. So we're going from x equals -2 all the way to x equals 2. That's a length of 4. Okay. So 4 for the base. The height goes from the x-axis, which is at y equals 0, all the way to y equals 8. Right? That's the function value at x equals 2. And so the height for this length here is 8. So multiply by 8 here. 1/2 times 4 is 2, times 8 equals 16. Okay. So that's the area of the two triangles. Okay. So given this, what's the net area? Well, by definition, you just add the areas. Whenever it's below the x-axis, you make it negative. Okay. So this triangle is going to have the triangle T2, which is above the x-axis. That's going to have positive area. So it's going to be 16. And then plus, well, minus the area of the triangle below, so -4. That simplifies to 12. Right, so that's the net area. So notice in this case, we are lucky that we can do it geometrically. Right? We can just separate this into 2 different triangles. And that's not always going to be the case, which is why we're going to develop this relationship between definite integrals and antiderivatives. But for now, we can do it like this, whenever it's a nice geometric shape. Now, that was the first part. The other one was the integral from 0 to 4, the square root of 16 minus x squared. And again, we want to graph this, okay? Because we want to find the net area. We want to do it geometrically. We want to find a picture of this. Well, notice first that we can identify, well, we could graph it as a square root function that's, shifted and stuff like that, or as a composition. The easiest thing is to realize that this is just a graph of a circle. Why? Well, if we let y be equal to the square root of 16 minus x squared, let's square both sides. So y squared equals 16 minus x squared. Add x squared to both sides. So get y squared plus x squared equals 16. What does that mean? That this function is just coming from a circle of radius 4. Remember that the formula for a circle is, let me do it in a different color. The formula for a circle is x squared, that looks too close to red. The formula for a circle is x squared plus y squared equals c squared, where c is the radius. Which means if we want to graph this on the interval 0 to 4, what is it going to look like? Well, it's just a part, it's 1/4 of the circle, right? It's the fourth of the circle that's in the first quadrant. Right? Circle of radius 4. It looks like that. So what's the net area? Well, it's the area bounded by the function and the x-axis. Well, since our function is positive, it's just this part here. Okay. So what's that area? Well, we already know that that's just 1/4 of the area of a circle, right? What's the area of a circle? It's pi r squared. Right? So, since the area of the whole circle is pi r squared, where our radius is 4, so pi 4 squared equal to 16 pi. Here we have 1/4 of the circle. So let's call this region here R. So what's the area of R? Well, that's just a fourth of the area of the whole circle, right? So that's a fourth times 16 pi, which is 4 pi. Now, this region is completely above the x-axis, so when we go ahead and find what the net area is, we don't have to worry about subtracting any areas, because again, if it's above the x-axis, you just take it to be positive. So this ends up being just integral, the definite integral of 0 to 4, a square root of 16 minus x squared dx. That's just giving you the area of this part of this fourth of the circle, which as we found is 4 pi. So as you see, in some cases, if the shape of the region that we're enclosing by our function, the x-axis, the region is simple enough, we can actually go ahead and compute this geometrically. Now, almost all of the time, that's not going to be the case. So we're going to need better tools for this. But for now, we can see some examples of how this works in the small amount of cases where we can actually do this trick.